Your lecture is about the LR1 parsing algorithm. The LR1 algorithm is used to build the parsing table for shift-reduce parsing, just like all the other LR algorithms we've been studying in the last few video lectures. The LR1 parsing algorithm is often referred to as the canonical LR1 algorithm to distinguish from the SLR1 table construction algorithm that we looked at in the previous set of slides. So let's look at an example grammar to give us some insight into where SLR1 can actually fall down and not help us with some shift-reduce conflicts. So here we have a grammar. We've added the usual S prime goes to S rule so that there's a new start symbol. L equals R, which handles inputs like this one, which is an identifier given a value of another identifier. And then you'll notice that there is this rule here. L goes to star R. This star is not meant to be multiplication. This grammar is assuming that you're doing some kind of pointer dereference. So you might want to use this one if you want to derive like a pointer dereference of some identifier equals some identifier, which you need to do in a C-like language. So let's see what kind of issues this grammar poses for the usual LR0 table construction followed by the SLR1 use of the follow set to make sure that we know when to reduce and when to shift based on the follow set of the non-terminal on the left-hand side of the rule. So let's take a look at the state 0 over here. State 0, you start with S prime goes to dot S, and then you predict all of the rules for S, which in turn predicts all of the rules for L and then the rule for R. Do the successor on ID, I end up with L goes to ID dot, and that state is fine because you can just reduce using the L goes to ID rule when you reach that state. Once you've reduced the L goes to ID, you go back to 0 and you take the transition on L and you move the dot across the L, and it happens to be two such cases, right? This L and this L. Now, if this was LR0, you would end up with a shift-reduce conflict because you have to reduce using this rule in the state, and you also need to shift on the equal to. SLR1 would tell you to do is to take the follow set of R, and if that doesn't contain an equal to, then there is no conflict because you would reduce in the follow set of R, all the symbols in the follow set of R, you would reduce on those symbols. And if equal to isn't in them, then there is no shift-reduce conflict. That's how the SLR1 algorithm would work. So let's look at the follow set for R. Where does R occur? Well, R occurs here, which is on the rightmost edge of this rule. L goes to star R. So the follow of R includes the follow of L. So what is the follow of L? Well, R appears here as well, as you can see. They're both on the extreme right. And so the follow of R also includes the follow of S. S appears here, so the follow of S includes a dollar, the end of input symbol, and so R, the follow of R must include dollar. And then follow of L, where does L occur? Well, L occurs here, which doesn't help because that means the follow of L is equal to the follow of R as well. But L also appears here, so there is this symbol that can follow an L. So the follow of R should include the dollar sign and the equal to. Right? So once I have a shift on equal to, I can move it across. The question is, what is the follow set of R? As we've just seen, unfortunately, it does include the equal to. So SLR1 is unable to resolve this shift-reduce conflict. So is this grammar irredeemable? Like, is it impossible to get a parsing table that doesn't have a conflict, right? So let's examine this grammar in a little bit more detail. So the problem, as we saw before, is that we want to decide to reduce this rule, R goes to L. And when we do that, we look at the follow of R, and the follow of R includes equal to. And so we can't resolve the shift-reduce conflict by looking at the follow set of R. Now let's just take a look at this grammar here and see where can equal to appear in the follow of R. Is it going to appear for every possible derivation that goes through R, or does it only happen in a specific situation? So let's look at the leftmost derivation, starting with the start symbol S prime. Let's look at some derivations starting from this non-terminal. And I'm going to show the derivation using a parse tree, just so that it's a little bit more visual. So S prime goes to S. I can expand this S to an R by using this rule. S goes to R. And then I can expand this R goes to L, as you can see here. And then L goes to ID. So if you look at this R goes to L rule, and what context can it be reduced, you look at what can follow this rule reduction. You can see it's the end of input symbol, right? It's straightforward because it's right at the right corner, right edge of this parse tree. Now let's look at a different derivation. S prime goes to S. And now we choose to use L equals R over here. And then I expand L to ID. R goes to L. L goes to ID. Now again, I'm looking at the context in which I can reduce this R goes to L. The context is a dollar. So in both cases so far, we've only seen the dollar. We haven't seen the equal to yet, right? In the context. In R goes to L, these two reductions both had the end of input symbol. Now let's look at another one. S prime goes to S. S goes to R. R goes to L. L goes to star R. So I'm using this rule for the first time. And then R goes to L and L goes to ID. So there's two reductions of R goes to L. This one and this one. And they're both on the right edge, so they both use dollar. So still no equal to yet. So how do I get a equal to in the follow of R goes to L in this parse tree? Well, I start with the S prime. I go to an S. And then I expand S with L equals R. And then I expand the L with star R. I expand R goes to L. L goes to ID. And this R goes to L and L goes to ID. So notice that this is generating the string that I mentioned before, which is star ID equals ID. Now if I look at R goes to L, there are two cases here, this one and this one, right? So this one does have the equal to in the context of the reduction of R goes to L, and this one, the second one over here, has the end of input symbol. So you finally have something which is about this equal to in the follow of R. But notice, so in a follow set, I would get both the equal to and I would get the dollar, right? I get both of these. But is this really a problem? It's not a problem if you keep track of how did I get to this R goes to L rule. The only way to get to this R goes to L rule is if I use this L goes to star R expansion, right? And that's the only place I can see this equal to the right of the L. If I have equal to in the context of the reduction of R goes to L, I must have expanded the L goes to star R, this rule. I must have used it in order to get there. As soon as I use that to get there, I know that I'll have an equal to. But if you look at this state 2, this state 2 is starting from S. And I haven't actually seen, if you look at the path to this state 2, there is no way that I had used L goes to star R in order to get to state 2, right? I started from S prime goes to dot S, and then I expanded that, and I got to R goes to L dot. I never saw this L goes to star R in order to get to this state. So if I can separate out the follow set of R into these two different contexts, one that includes L goes to star R, this part in its derivation, and only if you have that in your derivation, then equal to is in your look ahead. In every other case, it's always just dollar. So I just need to separate out the look ahead in basically split up the follow set into these two different subsets. One is dollar, which is most of the time, and equal to only appears if I use the L goes to star R rule. So the solution to this is called canonical LR1. So it still has one symbol of look ahead, but unlike simple LR1, it doesn't just blindly compute the follow set. It takes into account subsets of the follow set and keeps track of which subset is actually useful in a particular state in order to do a reduction. So we extend the definition of a configuration over the dotted rule. So when you have a dotted rule, before we used to have a dot on the right hand side of the rule, but now we're also going to remember the look ahead, the context in which we can do a reduce when we are ready to do a reduce. So it keeps the look ahead around in the dotted rule itself. Because of this extra piece of information, we also have a new closure method. The new closure method works just like before. We do the same predictions, etc. But now we have to take into account this look ahead symbol, which is part of the dotted rule now. And then we also have to extend the definition of the successor function to take into account the look ahead again. So the LR1 configuration looks like this. Configuration and dotted rule are interchangeable terms. So if I have a dotted rule, as you can see, there's a dot here in front of beta, and there's a new thing that's been added here. So this is the new addition in a LR1 dotted rule, where I've added a terminal symbol. So A belongs to the set of terminal symbols, and it's viable if there's a rightmost derivation, where if I'm taking alpha beta and replacing it with an A, right? So that's this rule over here. I look at the right context here. This eta here can be replaced with A gamma. That means that I can expand and find a terminal symbol that appears just after the handle that I need to reduce. So I'm taking this alpha beta, reducing it to an A, and I'm looking for the context in which that can happen. In that context, I look for the terminal symbol that can begin that context, and that symbol is what I'm going to put in here, into this. Working through an example is going to make this a lot clearer, but in a general mathematical sense, what we're doing is working through all of the derivations and looking for the context in which I can do the reduction, this reduce for this rule. And if this eta is empty, then the A has to be the end of input symbol, because there's nothing to the right. It has to be essentially the edge, the right edge of the input string. So what follows is the end of input symbol. The notation that we're going to use in the upcoming examples is just purely to save space. So if I have three different dotted rules, and if the dotted rule part of it is the same, it's just that the look ahead is different. So this one has a look ahead A, 2 has a look ahead B, 3 has a look ahead C, then instead of just writing it out 3 different times with the same, this part being the same. So this part is sometimes called the kernel because it's the part of the dotted rule without the look ahead. If the kernel is the same, then what we can do is collect all of the look aheads together and say that the look ahead is A or B or C, right? So this is just a shorthand to avoid writing the same kernel dotted rule over and over again. So let's take into account a fairly simple example where you have S goes to BB, and then this B non-terminal generates a bunch of A's using this write recursive rule, and then finishes the recursion by generating a B. So if you look at this B, it is generating A star B, right? It can have 0 or more A's, and at the end you have to have a B to terminate the recursion. Now if I look at this, what is the language of S? S is deriving B, so it can derive A star B followed by A star B, right? So this is the first B, this is the second B, right? So BB means A star B, A star B. Now if you look at the context in which I can do a reduce of the non-terminal in this part of the string, you can see that the look ahead will either include A or B. Now if I look at A star B again, and I look at a reduction somewhere here, if I want to reduce this non-terminal B here, the context will be the end of input symbol. So notice that here the first B will have the context of the second B as the follow. What can follow it is essentially the language of the second B. What can follow this one is going to be the end of input symbol. So let's look at how this works in LR1 table construction or the LR1 algorithm. So let's consider a derivation. I know that in 0 or more steps I can start from the start symbol and go to AA. I can end up with this symbol. So let's take this sort of fully worked out derivation. S goes to BB, BB goes, so essentially I take the symbol and replace the rightmost one with AB, and then I replace this rightmost one with a B, I replace this rightmost one with an AB, and replace this one with AAB again, and then I replace this one with an AB. Right? So this is what we care about here, is this reduce of this AB with this using the rule B goes to A. So if I look at this derivation, I've just summarized this worked out series of steps. I said in 0 or more steps I can get to a sequence where I have this AB being reduced with this rule B goes to AB. Now we say that this item B goes to A dot B in the context of A is valid. Notice that this context A is represented in this derivation by this symbol here. So when I'm doing that reduce action of AB being this AB being replaced with this left hand side of the rule, then I can do it in the context of this symbol A, right? Which is, I'm holding it in the, along with the dotted rule, this look ahead. So I can see that if I'm going to reduce a B of this side of the parse tree, I'm going to look at the look ahead symbols that are produced by this second B that will always be after the first one. Now let's look at a different derivation where it's the rightmost, this right, not the rightmost, but the right B. So here, if I have an AB and I want to replace it, again I'm using the same rule, right? But in one case, the look ahead is coming from here. In the other case, the look ahead is the end of input symbol. So in this case, you notice that the look ahead is the end of input symbol, the dollar sign, and it's valid for this BAA variable prefix. So note that I'm doing this reduction. This AB goes to B. And notice that the look ahead is the dollar sign. So in this BAB, this reduction, this string AB is called the handle, or the right-hand side of the rule. B goes to AB, right? This is the notation we've looked at before. So in LR1, the closure property is different from before. It's not radically different. It's just different in that you have to take into account the look ahead. And the way we do this is we start off with a dotted rule with a look ahead. And we're going to start with, S prime goes to dot S. And the look ahead is going to be the end of input symbol. And then we're going to take the closure of this, right? So every time we take a closure of a dotted rule, every time we take the closure of a dotted rule, it's going to come with the look ahead symbol as well. So in this case, the look ahead symbol is some terminal symbol A. If I have the dot before the non-terminal B, I predict all of the B rules with the dot on the left, sort of just initialize there on the left-hand side. The leftmost part of the right-hand side, right? So this dot is before the gamma. The gamma is the right-hand side of this rule. And then the look ahead for that is going to come by looking at what can follow this B. This is very similar to the follow, but except it's not taking the follow set on the whole grammar. Rather, it's taking the follow set from this particular rule and take into account this look ahead. So it's not just beta, but it's also A. And B is going to be computed by taking the first of beta A. So notice beta is the context just after this non-terminal B in the rule. The clever thing about this first of beta A is that if beta is the empty string, then you just inherit the look ahead directly from the look ahead of this dotted rule, right? And we'll see that this really makes it possible to make sure that you distinguish between the different look ahead symbols that you need in order to do the reduction. So this is much more fine-grained in terms of the look ahead than the SLR1, which was just computing the look ahead using the follow set. So notice that this doesn't just rely on the grammar, it also relies on the look ahead that's in the dotted rule, in this augmented dotted rule for the LR1 algorithm. And just as before, we compute as a fixed point, so we keep adding stuff. If we've already added it, we don't add it again because it's a set until we can't add any more dotted rules with the look ahead to my item set. And we only include contextually valid look aheads. And that means that if I'm in this particular rule with this beta, I'm not going to take into account all the other rules of A in order to take this into account. It's a specific rule, this specific rule, that's going to provide the context in order to tell me when I can reduce this rule, A goes to alpha, B beta. So let's look at an example. In order to look at an example, we'll start with the closure of the augmented rule. So we augment the grammar with a new start symbol, S prime, just like before. And the initial configuration set is S prime goes to dot S, and the look ahead is the end of input symbol, $. Right? So we know that when do I want to reduce S prime goes to S? If my dot ends up here, I know that the next symbol should be $, because I've accepted the entire string, so I'm done with parsing. So the next symbol has to be the end of input, Otherwise, I shouldn't reduce this, right? If I haven't accepted the entire string, I shouldn't accept it. So that's why I start off with the end of input symbol here as the initial look ahead symbol. Now this is the same grammar we started off before. We remember that we had tried to do SLR1 parsing for this, and we failed because it was unable to decide when to reduce R goes to L, because follow of R included the equal to, and the shift was on the equal to as well. So let's see if LR1 fares any better. So we're going to start with the closure. We start with the dotted rule S prime goes to dot S. The look ahead is $, and we compute the closure. So let's do that step by step. So we start from that one. Now we look at all of the S rules. So these are all the S rules over here. There's 2 of them. S goes to L equal R and R. So I put the dot on the right hand side. And the look ahead here is just simply inherited because there's nothing after this S, right? There's nothing following the S. So essentially what we did is we computed the first of the empty string followed by the $sign, and therefore we got the $sign here and here. Now the dot is before the L, so we look at all of the L rules. So notice that everything is exactly the same as the LR0, except that we have to keep track of this additional look ahead symbol. That's the only difference. So if you're familiar with the closure from LR0, this is no different, except that you're keeping track of this extra little bit of information, the look ahead symbol. Okay, so let's predict the L rules. L goes to star R. Now notice that this look ahead is equal to, and why is that? Well, if you look at this, we're computing the first of equal to R $, and the first of that is of course this symbol equal to. So when I predict this L rule, all of these L rules are going to get equal to as a look ahead symbol. Similarly, for L goes to dot ID, the look ahead symbol is equal to. Now I predict the R rules because the dot is before the R. And notice the look ahead here is $. So what we're going to do is, again, it's going to be first of epsilon, the empty string $, because there's nothing after the R. And when I predict the R, I get R goes to dot L $. And this dot over here predicts the L rules. Now I get L goes to dot star R. And here I'm getting first of epsilon $. Notice that these two have the same, if you look at the dotted rule, they look the same, but the look ahead is different, right? So in the LR1 construction, these two are considered to be different dotted rules because their look aheads are different. Unlike in LR0 where they would, there was no look ahead, so they would be identical. And then we have L goes to ID. Again, if you compare these two, they are identical except that the look ahead is different. And that's the complete closure. There's no other elements that we need to add to this closure. We've covered all the different non-terminals, including all the different look aheads that can occur. And as we showed you before in the notation of the dotted rules, we can concisely take all of these dotted rules, and instead of having these two different dotted rules with different look aheads, we're going to combine them together. So this is just a shorter way of writing the same thing, where we've taken the L goes to star R, these two rules, and we merge them together over here. So we just show the two look aheads that can happen. And similarly, we take these two L goes to ID rules and write them with the two look ahead symbols there All the others only have one look ahead symbol, so there's nothing, it can't be any more concise than that. So that's our first state. So let's talk about the successor function. So if I am at a configuration or item set and I have a symbol, it's either a terminal or non-terminal, and I want to compute a successor, then all I have to do really is, if the dot is before a non-terminal or a terminal, I just have to make sure that I don't forget about this look ahead. So the successor of an item set with non-terminal is I move the dot across a non-terminal and I keep the same look ahead. Similarly, if I'm moving the dot across a terminal symbol, it's exactly the same. I just copy over the look ahead. So successors are really easy. They're no different. The only thing you have to pay attention to here is that the dotted rule has a look ahead. You have to copy that over. So let's look at this example. We started off by taking the closure of s prime goes to dot s, and this is exactly the closure that we computed before. Now we take a transition on an ID. I look for the dot in front of an ID, and I can see that there is one over here. I move the dot across. I just copy over. When I do that, I just copy over the look ahead. So in this case, I can reduce L goes to ID in the context of either a dollar end of input or equal to. If I'm going to make a transition on the non-terminal L, I look for the different L's here. So this L and this L. And this was a case which was giving us trouble before, right? We ended up with a shift reduce conflict here because the follow of R included the equal to. But in this case, we are just going to use this look ahead. We're not going to use the follow of R. We're just going to look at this look ahead. It says you can reduce R goes to L if the next input is $, which is different from equal to. So therefore, there is no shift reduce conflict if I use LR1. So carrying around the look ahead helps us resolve the shift reduce conflict over here. On an equal to, I would move the dot across equal to so that I then have the dot before the R. I predict all of the R rules. R goes to dot L, and then L the L rules because the dot is before the L, and then notice that this look ahead is copied over everywhere, right? So this L goes to dot R has these two look ahead symbols. This one, L goes to dot star R, only has the $. So these two are quite different from each other. One of them can reduce in the context of equal to and $. One of them can reduce only in the context of $. And it came just naturally by just copying the look ahead symbol. Now if I move the dot across the ID, here I get L goes to dot ID with the $. Notice again, if you compare state 1 and state 4, they have the same reduce on the same rule, but the look ahead is different. In state 1, the look ahead is $, or equal to. In state 4, it's only $. So these two states are considered separate because they have different look aheads. So if you expand this out, this has two elements in this state 1. This has only one element in this state 4, right? If I move the dot across the L, I get a reduce, which is R goes to L dot, and this can be reduced in the look ahead of $. Or if I move the dot across the R, I get S goes to L equal R, and again the look ahead is $. Now if I move the dot across the S from state 0, I get S prime goes to S dot in the context of the $. So unlike in LR0, I don't have to assume that I'm going to only do an except if the next input is, the $. Symbol. Here the dollar symbol or end of input is carried along as part of the dotted rule. So I know exactly when to do this reduction. Now let's look at the dot being moved across the star here, and you're going to move to the next slide. So this is the same state 3. I'm going to have a successor function on the star. The dot before the R means I predict the R rule, which then predicts the L rule. And again, the look ahead is just inherited, right, when I do this. And the reason is because there's nothing here after the R, like we've seen before. When I transition on the R, I get L goes to star R. And this L goes to star R is only in the context of the end of input symbol. And if I move the dot across the ID, I get L goes to ID dot star. And L goes to ID, and I'm going to reduce using this rule, and the context is $1, right? So this step 4, let's go back. This is the same state that we had seen before, right? It's exactly the same. So let's forward back to where we were. Now I see an L. I reduce R goes to L, and this is also a state I've seen before. So if the state has the same dotted rule and the same look ahead, you're not going to create a whole new state. It's the same state as the one you saw before. And now on a star, you go and move the dot across the star, you'll get exactly the same state 8 as you got from transitioning from 3 to 8. Now let's take state 0 again and move the dot across the star over here, and I get a new state this time. So notice this is different from the state I saw before because the look ahead here inherits this equal to $, right? That's inherited from state 0 from that rule. And now it's sort of copied over to each of these. So notice that here I have L goes to dot star R with 2 possible symbols. In either of those symbols appear in the look ahead, I can use this. So if I take another star, I go back to 10. If I see an ID, now I see that L goes to ID dot. This is also a state I've seen before, but you can see that there the reduce happens in the context of either equal to or $. And again, there is a new R goes to L. The next step is to take the dot across the R. So you're taking the successor with respect to R, and I get L goes to star R, and I move the dot across. And again, the context in which I can do this is either equal to or $. And these are new states. Before the previous time, we could see L goes to star R was only in the context of the end of input. This state lets you do this reduce on both the equal to and the end of input symbol. From state 0, if I take an R, I get S goes to R dot. So I reduce with the S goes to R rule, again in the context of end of input. And if I take that automaton and write it down as a parsing table, the notable cases over here are state 2. You can see that on an equal to, you do a shift, and on the end of input symbol, you do a reduce using rule number 5, which is R goes to L. And another few notable cases are if I have S4, on an ID it shifts to 4, on a star it shifts to 8, and if you have 13, it reduces using rule 2, which is S goes to R over here. It only happens with certain symbols of look ahead. So this parsing table can now be used to drive a shift reduce parser, just like you would LR0 or SLR1. So all of those algorithms are purely there to build an action go-to table, which tells you what actions to do when you're doing shift reduce parsing. So LR1 construction, you construct these item sets, and if you have the dot on the extreme right of the right hand side of a rule, that means that the action is to reduce using that rule. And we're going to use the look ahead symbol here to put the action of reducing only for those look ahead. If I have the augmented context-free grammar rule, the S prime goes to S dot, then it's an except, which means parsing is done as long as the next symbol is the end of input. If I have a dot before a terminal, then the action on that symbol, this symbol A, is going to be shift. Right? To shift, if the successor of this item set I is equal to this item set J, then the action is to shift or push J onto the stack in preparation for a reduce action later. If the successor is on a non-terminal, then we put in the go-to table that if I have a I and successor on this non-terminal A goes to item set J, then I put in the go-to table from I to J, I put that in based on this non-terminal A. So that's going to help us when we do a reduce. We pop stuff out the stack, and then we look up the go-to table to tell us what is the next thing to push on to the stack to keep the parser going. All entries that are not defined are errors, and I0 is the initial state. So we always start from the closure of the S prime goes to dot S rule. And LR1 only reduces using a rule if A is the next input symbol and it's in the look ahead of the LR1 dotted rule. And LR1 states remember the context by virtue of this look ahead, right? It's carrying around this look ahead in the dotted rule. But one downside of LR1 is it might end up with much more states, so many more states than LR0 due to this look ahead. As we already saw in this example, in LR0, many of those states would be collapsed together, but here they can't be because their look ahead is different. And one practical way to reduce the size of this automaton or the size of this table, the action go-to table, is to use an algorithm called LR1. So in order to help you with tracking whether you're understanding it, I want you to write down the LR1 automaton and the parse table for this grammar over here, which we've seen before. And we saw that wasn't a SLR1 grammar. So I would like you to answer the question, is this a LR1 grammar? So the LR1 conditions are as follows. A grammar is LR1 if for each configuration set or item set, we have these cases. If the dot is before a terminal symbol, there can't be another rule in that item set. You need to do a reduce action, and the look ahead is the same as this symbol over here, because then that would be a shift reduce conflict for LR1, right? So even with LR1, you can end up with the shift reduce conflict. And if you have any two rules, A goes to gamma dot and B goes to beta dot, and if I have a look ahead A here and a B here, those look aheads have to be distinct. You cannot have them be equal, otherwise I end up with a reduce conflict. If you look at this set of grammars that you can write, there are LR0 grammars, which are a strict subset of the SLR1 grammars. SLR1 grammars are a strict subset of the LR1. LR1 grammars are a strict subset of LRK grammars with K symbols of look ahead. But if you look at the languages, there's an interesting property here where the languages expressed by LR1 are no more, LRK is no more expressive than LR1. Essentially, what this tells us is that you can always take a LRK grammar and then convert it because the languages expressed are the same. You can convert it into a new grammar, which is in fact LR1, and the languages would be the same. So that's what that result means. So it's a surprising result. It means that for LR parsing, K symbols of look ahead are no more powerful than one symbol of look ahead. And the idea behind this proof is actually quite elegant. What they do is they capture this extra bit of look ahead by changing the non-terminal. So each non-terminal captures this extra look ahead. And so by expanding out the grammar, you can take what needed K symbols of look ahead, you can now represent it with a new grammar that only needs one symbol of look ahead. So it's, of course, a proof of that is outside the scope of this class, but it's a nice, elegant result about these deterministic grammars. And it's interesting that adding more look ahead doesn't really make your formalism, what you're using to describe the syntax of programming language, it doesn't make it more expressive. So LR1 uses left context, a current handle, and look ahead to decide when to reduce or shift. It's the most powerful parser so far in terms of the table construction. It can handle essentially more context-free grammars. Like more context-free grammars can be converted into a shift-reduce parser without running into a shift-reduce conflict. LR1 is actually a practical simplification, and I'll explain what it does in the next slide. And it uses fewer states to avoid the very large tables generated by LR1. So it's used by Yak and Bison in order to make the table size a bit more manageable. The idea behind LR1 is quite simple. The main idea is if I have two states, 3 and 6 here, and they are identical except for the look ahead. So the look ahead in each case is different. Then what we can do is merge these two states. So I'm just calling it the merger of 3 and 6 is a new state where if you look at the core set here, they are the same. It was just that the look aheads are different. So I'm merging each of the look aheads together to create a new state. So what used to have, you needed two states before, now you only need one state. So by merging it, sometimes what can happen is you can introduce a conflict. So let's look at these two states. You have 2 and 4. B goes to, this has a look ahead of reducing using this rule in the context of C. This reduces in the context of E. This reduces in the context of G, and this one in C. So if you merge them, I get CG and CE, C or G, C or E. And notice that now what I've done is I've introduced a reduce conflict, and I can't do that. So this is not a valid merger according to the LR1 algorithm. So in LR1, the assumption is that the merging doesn't introduce any reduce conflicts. A shift-reduce conflict can never be introduced in LR because all you're doing is merging together these states, so you cannot introduce a new shift-reduce error. The merging can be done brute force. By brute force, I mean you can construct the entire LR1 automaton first, and then when it comes time to write down the parse table, you do the merging sort of by brute force. Essentially, you've already computed the larger automaton. You're just shrinking it so that you can create a smaller table for the parser generator. Or you can do it step by step. So as part of the LR1 automata construction, this LR1 condition can be used. And there's an efficient algorithm out there that modifies the LR1 automata construction in order to do LR1, which is the sort of pragmatic alternative to LR1 that is implemented by Yak and Bison. So it's more compact, and so the table sizes look more like SLR1 or LR0 for that matter, rather than the canonical LR However, it's still more powerful than SLR1 because you don't always merge to the full follow set. So that's what makes it more powerful but more compact. So it's a good trade-off to have in a parser generator.